I'm Michael Parks. I'm the director of the School of Journalism here at Annenberg. And my pleasure to introduce Casey Cole, a colleague at the LA Times, whose work I came to admire tremendously, particularly after I undertook to edit when everybody else had refused to deal with it, a multi-part series on string theory, which we published, much of it on page 1, to the extraordinary, to my mind, response to readers. We got more emails, more letters, and telephone calls on a series on string theory. Much of the work being done here at USC, than almost anything else I could remember of that particular, I thought, non-controversial character. So Casey's now writing a philosophical, intellectual biography of Frank Oppenheimer. She's on book leave from the Times. This is what, the 12th, 13th book?
Oh, no, not 9.
9. Not 9.
They're not all about science.
So she's beginning to rival Professor Cray in terms of sheer productivity. But we're delighted to have her here to talk about how a journalist, who's after all not a bench scientist, how a journalist writes with authority about things that by their nature are uncertain.
Okay. And I'm going to stand here just because we need to. Thank you. You should wait until I'm through to know whether or not I should clap. I will actually, when I get to the end, I would like to talk about the incident, although it went over a year with the series on the end of space and time, which Michael referred to. I was also told by people in the physics department that I'm supposed to inform you that this talk in no way overlaps with a colloquium I'm going to be doing next semester on science writing there. So I had to come up with something new, which was kind of a challenge. But also, I thought an issue I really haven't talked much about before, and that's uncertainty. It's a given that all scientific data is uncertain. We know that they're not data, but conclusions, theories. We know that there's more data out there. We know that there's always going to be new ways to interpret the data. We know that there are all kinds of ways that can muddy the results, which may not be obvious at first glance. But what people don't understand is that it's the fact that scientists both acknowledge and quantify uncertainty that makes science so strong. They have to say, this result is 99% certain. This one is only 80% certain. This survey or the information we're getting from this source is very clear. From this other one, not so clear. And there might be stuff coming in from sources we don't even know about. This doesn't imply that we can't have confidence in these findings. On the contrary, the most solid scientific knowledge we have may well be superseded at some point. That's what makes science different from religion, that everything has to be proven and proven and proven over and over and over and over again. I always like Einstein's analogy, where he talked about getting new knowledge as not tearing down an old house to build a new house, but keeping the old house and climbing a mountain so that as the higher you go, you can look back and your old house is still there, but it looks different. It looks smaller. The perspective is different. You see more and you see things around that you never saw before. And I think that's a really good analogy. So we have to deal with uncertainty, whether it's you're writing about string theory or whether you're writing about evolution. And it's incumbent upon the science writer to let the reader know the magnitude and the nature of these uncertainties, what's known, how we know what we know, and what we know about what we don't know. Now, physicists and astronomers make this pretty easy because they use error bars, they call them, in all the studies. So it's pretty graphic. I remember one time at the LA Times, there was a featured article in Science magazine, in the journal, that it's something about the moon. I don't remember what it was, but it sounded a little nutty off the top. Anyway, my instincts told me it wasn't much, but I looked at the little graph that came with the article, and you could see that the error bar was bigger than the result, which is sort of like saying, you know, Bush is leading Kerry by 2% in the poll, and the poll has a margin of error of 2%. So that really doesn't tell you much. And something like that happened actually in the study, the initial coverage, you may remember, of the effect of hormone replacement therapy and heart disease and cancer as well. People had thought, you want me to speak up? Even with the microphone. Is it on? Okay, good. I'm glad I'm standing. I know I have a low voice, but it's worse when I'm sitting. Okay. Okay, great. I didn't know that. In that case, I'm not normally a medical writer. I normally write about physics, astronomy, perception, things like that. But when that study came out, they were, of course, expecting to find that hormone replacement therapy lowered the risk of heart disease and some other things. As it turned out, there seemed to be a slight increase in risk. But the numbers were 8 or 5 out of 10,000. And those are really small numbers, which should immediately start ringing bells. And I started asking doctors I knew about it, and they said, yeah, those are really small numbers. We really can't tell very much from that. Now, that has changed. These studies have been analyzed, and it's much more clear now where the risks are, for whom, what therapies, what you have to watch out for. But the initial coverage didn't much take that into account. But small numbers are always an indication that you should prick up your ears. And of course, this applies to any field at all. It's like trying to convince you that I live in a very wealthy, wonderful neighborhood because half the cars on my block are BMWs, when in fact there are only 2 cars on my block. Or that it's very natural to get a string of 10. If you toss a coin 10 times, getting a string of 9 heads could very well be due to simple chance. But if you toss the coin 1,000 times and it comes at 999 times heads, you've probably discovered some new law of nature, or you know that your coin is weighted and not a normal kind of coin. So, but it's more than just statistics that can be, they can result in uncertainty. There are hidden correlations, and let me give you one example that was talked about a lot was the connection between proximity, people who lived near to power lines, and prevalence of certain kinds of cancer. Now that's pretty much gone away for 2 very good reasons. One had to do with there's no sensible mechanism through which electromagnetic radiation of that wavelength could cause cancer, could affect cells. Other wavelengths maybe, but not that one. But more important, the initial studies overlooked something very important, which is that people who live under power lines or very near power lines tend to be poor. And poverty always correlates with poor health, as does race. And that's very often messes up these studies. You have to be very careful that somehow they've taken account. But sometimes you don't know what those hidden correlations are. Just a little trick I'm sure all of you have heard, but I will tell you anyway, that there is a very strong correlation between shoe size and children's performance on math tests. This is an example John Allen Palos uses. It's because they're older. But you can equally argue it's the same with, fluoridated water. Cities with fluoridated water have many more cases of AIDS than cities that don't. But they tend to be bigger cities. So you have to be very careful of these hidden correlations. And physics and astronomy have to deal with those kinds of noise, but also lots of other kinds of noise. In a typical physics experiment, you have to throw out 99.9999 something percent of the data. You can think of it a little bit like sitting in a symphony hall, and it's very loud. Well, let's call it a rock concert then. Very, very loud. And somebody's trying to whisper a secret in your ear. And you can barely hear it. So, what's that? And they have to say it again. What's that? So the only way you can be certain is to have them repeat it over and over and over and over again. And the more they repeat it, the more the signal-to-noise ratio increases, and you have a better sense of whether or not you can have confidence in your result. But it's also easy to mishear when you're in a very noisy environment. You might mistake something that's noise. This also happens in every field in surveys as data. And a famous case of this, which you may remember, was a scientist who promoted for a long time the fact that most of the water came on Earth from comets, from big snowballs from space. Now, immediately, if you went on the web, you could see astronomers thought this was kind of silly, and there were already pretty good theories about how water got on the Earth. But as it turned out, the signals that he was seeing did turn out to be spurious signals in the detector. And that's not uncommon at all. In fact, one physicist who made a discovery based on too little data, a particle he called the upsilon, he wound up calling the oops-silon because of that, which I thought was pretty cute. Another kind of source of uncertainty that people don't talk a lot about is the hazards of extrapolation. Let's say in astronomy, for example, you're trying to figure out the distance to something. That the distance is all important because that's going to tell you about brightness and about size and therefore about the character of whatever it is you're looking at. But distance in astronomy is measured on what's called a distant ladder. If uncertainty creeps into any ring, you're in trouble. Now, one of the most solid rungs on this ladder are so-called Cepheid variable stars, because they're thought of to be what they call a standard candle. That's like a light bulb that says 100 watts. You know what its brightness is. So when you know that, it's very easy to judge how far away it is. But I was talking with Wendy Friedman, who's the director of Carnegie Observatories here, who did the most valuable and important work on these variables and measuring the universe. And she said, well, there's a lot we don't know about these stars. And, you know, there may be uncertainties. So extrapolation can be dangerous. The other thing you see people do is trends. There's been a rising in the rate of something for a long time, or there's been a declining in the rate, and it's implicit, or sometimes even it's explicitly stated that things will continue to go in that direction. That's almost never the case. Populations can run out of food or space, but it's even true in physics. If you drop something and the acceleration makes the speed increase faster and faster and faster, but not forever. It reaches a terminal velocity. You drop a feather and it'll get faster, and then it will just stay absolutely the same. So you have to be careful about those. In fact, you can't assume that anything will stay the same over changes in not only in time, but also in scale or distance. Physicists found this out the hard way when they probed deep inside the atom and found out that the laws of nature are entirely different there. Quantum mechanical laws, completely different than anything that was ever seen before. Also at really fast speeds, like if you're going near the speed of light, everything is different. So have to be careful of extrapolation. Let's see, what else was I going to tell you about? This is an interesting case in point. Uncertain things that I thought were absolutely solid. One thing I wrote about a lot about at the Times, because it was a big discovery. It's actually been the first time I've ever been around for a major discovery that was accepted rather quickly. And that was this so-called dark energy that is pushing the galaxies at the edges of the universe apart. It seems to be some kind of repulsive force. It's not anti-gravity, but it's something. Now, how would they know that? Well, the astronomers were looking at galaxies. They couldn't really see the galaxies very well, but they could see stars in the galaxies, a super kind of exploding star, a supernova, that they also thought was a standard candle, that they knew how bright these things were, so they could tell how far away it was. And it turned out that these were dimmer than they should have been. So they extrapolated from that, well, they're dimmer, they must be farther away. Well, of course, first of all, you have to be careful because something can be dimmer for a variety of reasons. Maybe there's dust in the way or something like that. And they dealt pretty much with the dust question. But again, I was talking to one of the heads of the teams, and he says, we don't really understand these supernovas all that well. So that introduces a very important kind of theoretical uncertainty into their models, because they don't really know if the whole chain of reasoning they're using might be based on certain false assumptions. Now, these days, the evidence for dark energy is a lot less uncertain. And this is a very important point. The reason it's a lot less uncertain is that evidence has come from an entirely unrelated source. That's the cosmic microwave background, the afterglow of the Big Bang, which you can read for all kinds of information. When evidence comes from two different unrelated sources, you can be pretty confident that it's true. When it comes from 3 or 4 or more, then you know you're really on solid ground. The final kind of uncertainty I'm going to mention is the fact that the way you conduct an experiment or ask a question has an effect on the answer you get. This is very obvious in the subatomic realm in quantum mechanics, where if you ask a little particle, I shouldn't even say particle, a unit of light, if you set up an experiment to say, are you a wave, it will say, I'm a wave. Just will behave exactly like a water wave or any other kind of wave we know. But if you set up an experiment, as Einstein did, it was one of his first papers, to ask, is light a particle, it will tell you, I'm a particle. And the same thing is true in relativity. If I want to measure how fast a clock is ticking on one of the GPS satellites that are overhead right now, it's going to be different depending on whether I'm standing on Earth or whether I'm on the satellite. So these things make a difference. And it's a little bit like a poll. You've seen these, you get certain results, and they say, but if you ask the question a slightly different way, you can get a very different result. One really obvious example is, if I were to assume that the Earth were stationary, I'm on a stationary Earth, it sure looks stationary to me, and I were to plot our orbits of the planets, I would get these curlicues, these epicycles, which is what people thought existed for a very long time. But if I assume that the Earth is orbiting the sun, now I get nice ellipses. So I get a very different answer depending on what my frame of reference is. So it's important to ask why scientists asked a question in the way they did and why not another way. And if they asked the same question another way, would they get the same result? That said, it's just as much of a sin to overplay uncertainty as to underplay it. And a kind of sad example of that is the coverage, I think, of the so-called controversy, well, I guess it is a controversy, between evolution and intelligent design, which is not science by any means. And you usually have to read to the jump of most of the stories to get that. It's not enough to tell the readers, which most of, even the good stories do, that the vast majority of the scientific community actually believes in evolution. Jon Stewart actually did a whole series last week. I don't know, did you see it on evolution, and he asked, well, these are kind of a Consumer Reports of science, where you can go and say, this theory has 3 stars, and that one has 5 stars. And there is actually, the National Academy of Sciences. But I don't think that's enough. You have to give the reader the reasons why it's certain, and it's easy in something like evolution. Or missile defense is another example where you hear people say, yet another test failed, and it'll say, proponents say, and they'll say, opponents say it will never work. Well, it's not opponents, it's the physics community. It's just about everybody who's not in the business of making this system. So, in one sentence, in terms of evolution, you can click off the fossil record. That's just one. Morphology, embryology, DNA evidence, which just spells out very, very clearly our relationships with other species. We do share about 50% of our genes with bacteria and about 98.5% with chimpanzees. I mean, there's just no question about that. And actually the same is true of missile defense. You have multiple lines of evidence, one being that what they're trying to do defies the laws of physics, but other than that, none of the tests have worked. But it's also true in places you wouldn't think, like the Big Bang. This is a really solid theory. Why? Because evidence comes from 3 completely unrelated sources. No, it didn't initially, but now, and that's why it's taken by almost everybody, I would say, as a given that it's true. An example where the press really messed up on underrating, the certainty, on underrating the certainty of something was, you may remember stories that the speed of light had been exceeded. The speed of light is so ingrained in the fabric of the cosmos. It's not just something people measured. It comes out of the basic laws of electromagnetism. It has to be the speed it is. Couldn't possibly be anything else. So it's a very, very solid thing. So when someone says that they've exceeded the speed of light, you have to be extra suspicious. And most science writers weren't. And what had happened was the overzealous press officer at a university had, and certainly with the help of the scientists themselves, had played games with semantics. I mean, they had a pulse of light, and certain wavefronts went faster than light, but others didn't. But it was really a game. The basic speed of light that we all think about when we're all talking about speed of light was not exceeded. So, ding. So how does a science journalist cope with all this uncertainty, or any journalist, I guess, cope with the uncertainty? Most of the time, it's just common sense, asking those simple questions I've talked about. What's your margin of error? How does it compare with the magnitude of result? What else could have caused the result? What hidden correlations might be at work? Are there any other lines of evidence that support or conflict with the finding? Why did you ask the question that way? Could you have asked it some other way? Again, has anybody else asked it another way? And if so, what were their results? The best questions are often the simplest. My mantra for science writers is always, dare to be stupid. I can't tell you how many times I have hesitated at a press conference. I always tend to overcome that, but to ask what I think is such a simple, obvious question that I must have missed something, and it turns out to be key. That happens over and over and over again. Journalism isn't passive, even in science, right? Little birdies sitting there with our mouths open, waiting to, get pre-processed information from somebody else. Now, obviously, a science journalist doesn't have time to analyze every claim. You're on deadline, and you've got some experts, people are telling you things. So what do you do? Other than having really good sources you've developed that you can call on a moment's notice, a lot of them, so you're sure that at least several get back to you, and not everybody on the same experiment. Bad idea. And most science reporters cover all sciences, which makes it really hard. They cannot be experts in a certain field. So what can you do? Fortunately, it's very easy to get a sense, a feel of every science by reading a single book. If you read 6 books, you will feel comfortable in it. You have to have somebody guide you to those books, but in medicine, in chemistry, in physics, in astronomy, and you get a sense of what kinds of evidence do they rely on, where do things tend to go wrong. and how people judge validity. In fact, it may even be easier in science to gain expertise because there are so many really good popularizations by really good scientists, most of them. But ultimately, the science journalist has to learn to live with uncertainty and ambiguity. And this is partly what happened with this story on the end of space and time and strings. And it had happened to me again. In fact, I was just doing a radio, it was a joint interview with Tim Ferriss, who you probably know is a very well-known science writer. And I was so glad to hear him bemoaning the fact that editors, it's a story he has not been able to get into the New Yorker, which he actually admitted, which I was surprised about. But because editors want to be able to understand what you're talking about. I don't understand it. You say, well, nobody understands it. That's what makes it interesting. That's why the scientists are there. If they understood it, they wouldn't be investigating it. But it's very, very difficult. And my personal theory is that most of these editors have been, Rhodes Scholars or used to getting straight A's and being the top of the top. And it makes them very uncomfortable to be dealing with something that they don't understand and things they don't know. Okay, so I'm going to conclude and let you ask questions just by saying the most important thing is understand yourself and point out to your reader, how do you know what you know that you don't know, what parts of what you know are solid and why, and what parts of what you don't know are shaky and why. As the physicist Richard Feynman once said, science is a long history of learning how not to fool ourselves. So I thank you, and I invite questions.
Basically, I'd like to ask a practical question. You alluded to intelligent design. What are we as journalists going to do when the Senate Majority Leader, a medical doctor, you, or the President of the United States says, well, you should teach intelligent design in the schools? What do these journalists do? Say, you're nuts, you're wasting time?
No, I mean, the argument is that it's not science. It's not science by any standard. So if they want to teach intelligent design, that's perfectly appropriate in a course on culture or something like that, society, even science and society, but not when you're teaching biological science and evolution. And those are the facts. So if the president is wrong, he's wrong. And he's really wrong on science, as I'm sure a lot of you know. Scientists are up in arms. I've never seen anything like it against the Bush administration because they destroyed science. In fact, I was listening this morning coming into the announcement about the NASA initiative to go to the moon and Mars. At least the New York Times had some analysis of why this might be a problem going in financial terms and competing priorities. But what you're not reading about is that here's how physicists and astronomers decide how to spend their money, because projects are really expensive. They all get together, they do these decadal surveys, they fight with each other about which experiments they should concentrate on, which are most cost-effective, which are going to bring in the most important results, and they write these reports and they present them. And this was done, and it was accepted by Congress, and basically when Bush came along, threw it out the window. Why? Well, if you look at the panel that was cooking up this Moon-Mars mission, the only astrophysicist is the director of the Hayden Planetarium, who hasn't published a paper in 20 years. The majority of the rest were heads of aerospace companies. So people at JPL were beside themselves. Where is the science? Now, I heard on NPR coming in, Larry Mantle was pretty good. He was raising this, and the response was, well, people get more excited about having people out there, real human beings and robots. First of all, I don't think that's true anymore with the Hubble Space Telescope, and when you look at the tremendous response to having the robots on Mars, things have changed since we went to the moon a lot. But in addition to that, then they turn around and say, well, aren't people going to be kind of bored? I mean, we already went to the moon. What's the point? And they said, well, yes, it'll probably be hard to sell to the public. And you want to go, what? Okay, so we're going to Mars, so that's the big deal. What's the most efficient way to go to Mars? Not to go to the moon first. I mean, it's just so there's no leg, there's no standing for this. This is what I mean by asking really simple, I think if you ask the person on the street to react to this announcement, their first question would have been, why? And that's the question that hasn't been answered in a lot of the coverage. Mm-hmm.
Casey, besides wanting to know what those 5 or 6 books are, have you been too modest in the demands that you think journalists who want to be science journalists need to meet? I mean, to what degree is actual coursework and discipline required to learn basic science, basic math, basic physics in order to do this kind of reporting?
Well, you're talking to a political science major who covered Eastern Europe and then wrote about women's issues and humor and travel and dogs and everything else, ballet, for many years before I even got into science writing. In fact, the way I broke into science writing was pretty funny. The New York Times offered me the Hers column. Does anybody remember that? When they used to, it was wonderful. They featured women writers and they gave you 9 or 10 weeks as long as you could produce. And so I said, here's my opportunity. I wrote all of them about physics. And I did hear later that Abe Rosenthal said he thought those were the best Hers columns, but I can't I have no other line of evidence for that. Did I answer your question?
Well, if that means that you never took calculus.
Never. I was a calculus dropout. Not a beauty school, but a calculus dropout. Because in the days when I was in school, I hesitate to say this, but I was very good in math, and calculus was the first time anything was hard in math. And my teacher said, oh, come on. She said, why bother? Girls didn't, and there were no other girls in the class. So, the message was, why bother? Had it been today, I probably would have taken. But no, that's what I say. It's really easy to get up to speed. It's really easy to get up to speed. Although I am distressed that more and more outlets don't think that any background or requirements are needed in order to write about science. That's not a good idea. Somebody needs to know a little bit about it, whether it's the editor, that's good enough, or whether it's the reporters who can act as the experts. But somebody who just can give a sense of context. It is asking a lot, but I don't know. I don't think reading 5 books is a lot, do you?
No.
Yeah. If for anybody who wants a list, I can email them or put them on the web. I want to think about that. But most of them are books by scientists. For example, Lewis Thomas's books, like Lives of a Cell. First of all, it's beautiful writing. I think I learned more about writing from Lewis Thomas than anyone, just reading. He's just lovely, 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 lovely. But whereas he doesn't give you a lot of facts, it's not the facts that are important. He gives you a real sense of what biology is. Really good. And that same is true in other fields. So I'll do that. I'll be happy to do that. Yeah. Mm-hmm. Uh-huh.
Yeah, you mentioned using a lot of books or reading up on the material. To what extent do you use scientific consultants in your writing to look over your articles to make sure they are, scientifically valid?
Well, the law is you're not allowed to do that. You're not allowed to show the article. In fact, when I wrote for the New Yorker, you have to sign this 35-page contract that assures you're not going to do that. Most science journalists don't pay a whole lot of attention to that rule when it comes to the really nitty-gritty parts of what they're writing. They usually do run it by someone. With books, it's easy. Books I run by at least 5 scientists, because that's forever. That's not something somebody's going to roll up and throw in the garbage. But it's a little bit tricky because you have to find a way to do it without getting fired. I mean, you can double check facts, but it's not the facts. It's not the facts that get people in trouble. It's the context that gets people in trouble. It's the understanding of the context. And you could say the same fact, and it means something entirely different in a different way. Mm-hmm.
How do you deal with the attitude in, say, the news today that anything has to have both sides presented? You know, if you're going to talk about somebody saying there's global warming, you have to have somebody saying there is no such thing as global warming.
It's a huge problem. What can I tell you? I mean, I got into journalism because I thought it was about telling the truth, not presenting two sides of issues that other people were telling you about. It was to go out and find out what's really true. And when you do that, it's not balanced. Usually journalism isn't balanced when you go out and find out what's true. Surely you should have statements from the other side, but I think it's really gotten out of hand, and it certainly doesn't apply to science, because science works on consensus. In theory, when it's accepted, it's accepted before a jury of peers. It means that you've convinced your colleagues that this is correct. That takes a lot of doing. So there's not another side. I mean, you could have, so-and-so says aliens landed, and somebody else says they did. I mean, it's just stupid. Anyway, I don't always win. In fact, I lost big time. I did a big article for the LA Times and some of the issues I was telling you about the Moon-Mars mission, but also about the fact that Bush has fired every civilian review board and consultant he had on nuclear weapons issues, which is pretty scary. And I was told I was going on leave, so it was a little tricky, but that it was unbalanced, and there had been too many anti-Bush articles in the paper already. So you didn't read that article. Mm-hmm.
Other than the high school calculus incident, I was wondering if when you started out doing science as a woman, did you come up against extra, I don't know, problems?
Oh, yeah. I was named KC initials at birth, basically. My name is Karen Christine, but I've always been called Casey. But it came in very handy. Because people didn't know who I was. But I would get these phone calls when I was an editor at Discover's, asking to speak to, Casey Cole, and I would say, this is she. And there would be this long silence. And once I was asked to give a university lecture at Princeton based on some writing I'd done. And that was a big deal. I got to dinner with the president and all of that. And it was one of the few speeches that my husband actually did come to. So when they kept asking when my husband was arriving, it never occurred to me that they thought that was So it comes up a lot. It really does come up a lot. What you have to do is just, in the first 5 minutes, you just have to establish that you really know what you're talking about. Not that it always matters. I will never forget, and I wrote a Hers column about this, sitting around a table at UC Berkeley, as it was then, Cal now, with a bunch of science historians. And boy, I really knew what I was talking about. I was so smart. I was just, when it was all over, one of the professors turned to me and said, "So, Casey, what do the women think of Carl Sagan?" Uh-huh. Oh, okay. Yes?
Without a science background, how do you actually learn to report on science?
Well, as I said, it's pretty easy to get up to speed. And by the way, the books I'm telling you about are as much about writing as they are about science. They're delightful, most of them. And it's just really not that difficult to get a sense of the field. Just a sense, of how it operates, of what the basic things are you need to know. It's not a whole lot, and it's really not very difficult. So that would be my answer. Mm-hmm.
Do you have a...
Oh, wait, can I just add to that? And then, when you're doing stories, especially beginning reporters in science writing, I find, get very intimidated about asking those obvious questions. You're sitting there and they're thinking, but wait a minute, what about, this doesn't make any sense to me. And you think, well, it's because I don't know anything. Ask the question, because that's the way you're going to learn the fastest. That's probably a great question. Mm-hmm.
I have a hard and fast rule that a scientist, and I'm thinking of mathematics here, but should be able to explain to you, a science journalist but not a scientist, what and why they're doing what they're doing. In the case of mathematics, often there's a lot of mathematics that's not grounded in the real world.
Right.
So I wonder if you walk away scratching your head saying, that's him or that's me?
Oh, yes. In mathematics, absolutely. I was the first fellow at the Mathematical Sciences Research Institute. The acronym spells out misery. And I had a terrible time understanding what was going on. But here's how I found that it works over time. You're talking to somebody, and I usually do this with a graphic. You're talking to somebody, you don't understand a word they're telling you. So it's like there's a little line here, there's another little line here, there's another bit there. But pretty soon it begins to fill in. When you talk to enough people, you get enough different pieces that it just, so what's hard is sitting there talking with someone and feigning interest or having interest when you don't have a clue what they're talking about. I really like challenges. So I think at the LA Times, when I was working on the staff full time, I was asked by the math section of the AAAS, the American Association, Science, to give a talk on writing about math. And I went through, and I had 40 stories on math in the LA Times over a very short period. A lot of them front page stories, many of them front page stories, just because I wanted to, And so, for example, the head of the UCLA math department just called me out of the blue and said, why don't you come over and see what we're doing? I thought, okay. It took a while to figure out what the story was, but it was a column one. So.
I wanted to ask about scientific consensus again. In the context of global warming, there's a great deal of concern about the word consensus in the scientific community. And James Schlesinger had a op-ed piece in the Wall Street Journal in early August where he attacked the whole idea of scientific consensus and said it really doesn't work for policymakers and government because some of the greatest scientific breakthroughs have been done by people who were outside of the consensus. And he referred to Einstein, for example, and had several other examples, and said that it's really there is no such thing, he concluded, as scientific consensus. And if we're trying to do that in the context of global warming, we're just kidding ourselves.
Okay, as soon as Einstein's papers were published, almost, within a couple of years, they were accepted because it was so clear that what he was saying was correct. So you almost immediately had a consensus. And on lots of aspects of global warming, you do. On a lot, you don't. I mean, it's a tough issue because one of the things I actually wrote, I guess I really like uncertainty, I wrote another column one on this for the Times about the subject of clouds. People really don't understand the role that clouds play because they both trap heat, but they also reflect it. So it's having more cloud cover. What's the effect of that going to be? There are uncertainties, but here's an argument that was made to me that finally tipped me over into the we should do something about global warming side of things. If we're wrong, and if there is global warming, it's going to be too late to do anything about it. It's going to accelerate so fast, and the effects are going to be so devastating that even if there's a chance that this isn't right, we just can't take that chance.
I asked your pardon because I wasn't here the whole time.
Okay.
I heard you mention Lewis Thomas, and my question is about your interest, access to biomedical. And because you mentioned Thomas, it makes me feel that you want to include not just science, technology, but that you you might reach
Medicine?
toward biomedical?
Sure. Well, I mean, one of the big trends in science is becoming harder and harder to separate out one field from another. I mean, they're all really interconnected. And I mean, for example, when I was teaching at Wesleyan, I co-taught a course with a biophysics professor. I brought in the writing because it helped students know what they were talking about. The biophysicists do a lot with the shapes of molecules, and because that determines how they interact. And that's very important in medicine. But it also has a lot to do with physics. So actually, I was just asked to give a keynote address to the USC Department of Kinesiology. Yeah, coming up. And I love that stuff. I mean, I'm interested in everything, alas.
Casey, you talked about basically sometimes people are fooled into accepting as.
Oh, yeah.
When were you fooled? Tell us about when you bought one. How that happened.
Oh, man. This is not a question I've been asked before. Surely I've been fooled.
This is that time.
Yes. I may actually have to think about this. Yeah, okay, I know one. I was at CERN, which is a big particle accelerator laboratory. It was really fooled, but it was in a way. It was very embarrassing, actually. Times flew me over there. They were looking for something called the Higgs particle, which is a chip off the old vacuum that everybody's trying to find. If you can study the vacuum, then you know everything about everything. And I went to dinner with a physicist who told me, well, here was the thing. They had this accelerator, and they needed to rip it out in order to build a new accelerator, which they're building now. It's under construction. But the people who had done this experiment, and they thought they saw real signs of this Higgs boson. So clearly they didn't want to tear out the experiment because they wanted to confirm their results. So it was a real tension between the two groups. And I had dinner the night before with one of the physicists, young guy, who told me unequivocally that they were not going to tear it down, that they were going to give them 6 more months to solidify their results, and that he got it straight from the director of the laboratory. So I wrote my story, and at 7 o'clock in the morning, my time, I go to sleep. The next morning, Yanni announces that, in fact, he's going to rip out the accelerator. So I was wrong. I guess I need multiple lines of evidence.
Did you attribute it to that individual who told you that?
Not by name. Or, I don't remember. I'm sure I had quotes from a lot of people. I thought I had this great scoop. I did, but it was wrong.
What about cold fusion?
I never covered cold fusion. I never bought that for a second.
Who did, and why did they get it wrong?
Well, I think because people don't ask simple questions. If you think about what fusion is, it's what lights stars. So how are you going to do it cold? I mean, that's the person on the street kind of question, and it's very difficult to do. Now they've done something that might be a little bit of this at UCLA, but in such controlled circumstances, I mean, nothing that you could ever get energy out of. It just didn't make sense. I call this a BS detector that you just have to develop in any field when something just doesn't sound right. It just doesn't.
Could you, Michael mentioned the reaction to the string theory story. Could you talk about some of your reaction to your stories in Science and Math in a popular newspaper? Is this an area that the press should be more in because of the interest of the readers?
Well, you're asking the wrong person. I have a little bit of a bias here. Yes, I mean, when the Times killed its science section, and I used to have a regular column called Mind Over Matter, there were hundreds and hundreds of letters from readers who were just really outraged. And I always got a lot of letters on stories, no matter what they were. What we used to do in the good old days, when we had Michael Parks around, was you would write yourself onto page one. I mean, I presume that people aren't interested in science and don't know anything about it. I presume that it's my job to make them interested in it. I don't know why that's not happening anymore. There are wonderful writers. Well, I better just being taped. Yes, I think the problem is, and this also came up in this interview with Tim Ferriss, and I think any science journalist will tell this to you. The problem is in the middle layer. The editors don't like to be confused. They don't like this stuff. They're uncomfortable with it, and they don't realize the reader reaction. Readers love it. Science museums are the most popular kinds of museums. Science books sell very well. Science magazines never been a readership problem. It's always been an advertising problem. People really like to read about this stuff. So, but there's this barrier. So I guess a part of the job of the science reporter is talking the editor into doing the story.
Probably take one or one question.
Well, I'll ask questions. Since you were a journalist, after all, it's a more general question rather than just about science, but it pertains to science in the following sense. From your point of view, is it the job of newspapers, for example, to let people know what's happening or let people know what they need to know? In the case of science, you see, it may be difficult for people to understand what's happening, but it's important perhaps for people to understand science since they don't understand.
You mean as science education,
well,
basic?
For the point of view of science. I mean, it's more general for other kinds of things as well.
I don't think they're really separable. I know this is a debate. It has been in the science journalism field. I remember we had a big conference on this, and the person who was the editor of the main sort of layperson section of Science magazine said, it's not the job of a science journalist to educate. It's the job of the science journalist to tell people what's new. But the truth is, you can't report on almost anything without reviewing the important facts about what's true behind it. You just can't, because out of context it doesn't make any sense. So what they need to know and what's important, also there are feature stories on what they need to know. I mean, there's always a peg. You know, whatever field, whatever you think people need to know about, there's always a news peg. There's always somebody who's doing forefront research on it. I mean, it just always is a way to make it into news. We're very sneaky. Okay.
Join me in thanking Casey.
Thank you.